So the system I wanted us to convert to matrix form would be the fourth order system that we defined previously. So we're going to convert this system here that we found before to matrix form. And there's a few things we got to be careful with in this setup, namely this t-squared term. I'll have to show you how you can properly handle that because it is a variable that isn't being defined by a change of variable. So this is something we need to be very careful in dealing with, and I'll show you guys how to watch for those types of scenarios. All right, so let's go back down a bit and let's begin. So let me go ahead and just make sure we create some differences here. So in this section, the way we begin is just like before. We create a column matrix, and it will be x prime 1, right? This was 4 different variables that we had to define since it was fourth order. And then x prime 3, and then x prime 4, okay? And this is going to be set equal to a larger system. This will be x2, okay? X3, all right? X4, and then finally, minus 8 x1 plus sine of t x2, okay, minus 3 x3, okay, plus t squared. All right, that's pretty straightforward. And then we can take this one step further, and I can show you guys what you do with this t squared term, okay, in order to truly separate out the column matrices in a way that makes linear algebra work much more effectively when working with variables that are not part of your change of variables. This is what you would have to do. This equals, meaning this piece here, this will equal another column matrix, which will be x2, x3, x4, and again the minus 8x1 plus sine of t x2, okay, minus the 3 x3, okay? So we've isolated all the terms that had changed variables incorporated with them. Now, to deal with this t squared term, this is all we need to do, and you'll see why this makes sense when you look at the matrice, when you look at the column matrix. The first 3 entries for this one will have to be 0, 0, 0, and this last term has to be t squared. And you can see that when you add each of these elements row by row, it gives us back the previous matrix. And this is how we handle terms that are not part of the change of variable. We have to add them separately outside of the column matrix itself in order to get the proper form. Okay, so we're almost done with this problem. So now that the first vector can be written as a matrix multiplication, we can leave the second vector standalone, which is what we have here with the t squared term. So as before, we're going to let x be, and you don't have to say this each time. I'm going to assume that your x vector implies the column of unknowns, but I'm going to assume this is true whenever you use that x vector, but you don't have to do this each and every time, okay? Right, so this would then imply, and so this is let, for example, let this be true, then the derivative, right, would have to be x1 prime, x2 prime, x3 prime, and x4 prime. Let me go ahead and make that column matrix more readable. Okay. So now that we have that set up, we can then finish this off by writing out what the final expression would look like, which would say x column matrix prime of our unknowns is going to equal, and this is where things become very interesting, because I want you to realize that here x2, for example, is the only entry that has a positive coefficient. There are 3 other entries here in this matrix, right? And in fact, it's there's 4 columns because there's 4 unknowns, right? So we need to be able to enter some coefficients for those as well, and you can guess what value that would have to be, namely 0. x2 has a coefficient of 1 in that first row, and then 0, 0. Okay, so that answers that mystery. And the next one is x3, right? So that occupies actually the 3rd position. So that's 0, 0, 1, 0. And then likewise, x4 is actually the 4th position. So that'll be 0, 0, 0, 1. Okay? And then last but not least, we have our 4th row, which has an x1 term, an x2 term, 3 term, but there's no 4th term. So this would be -8 is the coefficient here. And then we actually have a function, sine of t, as our coefficient here, -3, 0. Okay, since the 4th variable was not present. This will be multiplied to the x vector that we defined, which is our vector of unknowns. And when you do this correctly, you'll get back this result that we had before. Okay? But we're not done yet. This also has to be added to that column vector up here to include the t² term. So this will be 0, 0, 0, t². All right? And that is almost done. Now we have to include the IVP, which will simply say that in our column of unknowns, the IVP has to be 1, 2, 3, and 4, which corresponds to x1 of 0 equals this, x2 of 0 equals 2, x3 of 0 equals 3, as you guys remember from before. Okay? And this will complete the problem. This is how you finish writing out the system. Okay? Now, there are some other techniques that mathematicians will use and engineers will use to write out systems like this in a more general form. And the way they do that, to make it easier to read or more condensed, is they will say, okay, my column of unknowns prime, my derivatives, is going to equal my coefficient matrix A, right? And so this is considered to be the coefficient matrix A, multiplied to my x vector, as you see up here. It's the same thing. But then they include an addition for this additional column matrix. And they usually call this G of t. Okay? And so they'll sometimes write it out this way just to make the notation easier to read and also to make the solution process easier to follow. All right. So there's just a couple more definitions I want you guys to understand from this last result. It would be the following. We say that the system is homogeneous, and this is a pretty neat definition that follows from this general form. The system is homogeneous if g of t is equal to the 0 vector. It's 0 everywhere. Then it's considered homogeneous. So this system, notice that there's zeros in 3 entries except for 1. This would be actually a non-homogeneous system. But if t² was a 0 entry, then it would be homogeneous. So if g of t is 0 everywhere, that implies it's homogeneous. Okay? And then likewise, if g of t does not equal the 0 vector, like in our example, that implies that it's non-homogeneous. Okay? And what's neat about that observation is that if we know a system of linear equations is homogeneous or non-homogeneous, there are some clever techniques we know about rank. There are some clever techniques we know about row space and column space that we can use to solve these systems more directly. And this is where linear algebra becomes a very powerful tool in solving these coefficient matrices for us. All right, so in the next video, I'll show you guys how to solve one of these together. Stay tuned.